Good evening mga Bisaya. So in this video we will be discussing lateral force resisting system. So diaphragm, bracing, shear walls, moment frame or Polter frame, and then wind column. So the last video we did was about load path. Actually these are just related, but um, we will be discussing load path for the lateral loads. It's either wind or seismic. So, so I already have this in mind, like basically at the very start, like discussing this one, and then last Saturday I got this message from one of the members group, and then it's I was actually shocked that with this question he was asking like basically when is he going to use cross bracing for the roof because he said mostly the roofing supplier comes with cross bracing already, so it's like a package because when he did the analysis for the truss for the roof, he said he only analyzed like one truss. So first, I have here I basically just downloaded. I mean, except this photo because this is one of our projects. But this one, I just downloaded a different like different types of lateral force resisting system. So first, we will discuss. So basically, I think when he asked for like when he, I would assume because I asked him, do you have a roof diaphragm? And well, it's unfortunate that he how do I say it? Like basically, he has no idea what the diaphragm is. So, or maybe he has an idea because when he modeled it, he um, assigned a diaphragm, like the notes for the diaphragm, but didn't realize that on the roof, if you don't have a roof diaphragm, then the transfer of load is different. So on this one, in this video, we'll be discussing how the lateral loads are transferred from your structural elements down to the foundation. Now, for the types of um, what you call this one lateral force resisting system is we have the bracing, we have the shear wall, and then this one moment frame and wind column, and then all of this is basically or the force will be transferred most of the time to your diaphragm and then to your bracing or shear wall is it or moment frame and down to the foundation. So I prepared these pictures here. So first we will discuss about um uh, which one we should start first. So this one, it's pretty straightforward. So basically this is a commercial building we did back in 2016, I think, or 17. So because this is a commercial building and then the owner doesn't want any visible cross bracings like in any of the walls. So because these are all like not all, but I would say 90% of the walls are curtain walls. So this one here, these are all like storefront, like glass, like full height glass. So I designed this as a movement frame. So basically, if you have so in this one, how the loads are being transferred um, or say applied, like you have wind load or seismic applied to the building and then transferred back to the foundation. So basically, you have a, for example, so this is your like one of the base, right? That one. So this is moment frame. So this is fixed right here. Oh no, was it fixed? No, I did not use a fixed support here. What I did was this is pin connection, this is pin, and this is the moment connection there. So it's more of like a portal frame um, analysis, portal frame system. So basically, so you have walls in here, right? So you have walls, and the walls are made up of um, curtain walls. So you have mullions, vertical mullions, which is the main structural element for the curtain wall. So well you have the um in designing the mullion or sizing the mullion, you have to use the components and cladding, right? Components and cladding. So we already discussed about this one. So it is applied to the glass and then it will be transferred or resisted by the mullion. Now this is, shall I say, this is height h, right? So half of that, so this is h over 2, this is also h over 2. So once the load is applied to the um, to the mullion, usually it's aluminum. So half of that load is basically this mullion is more of like a vertical beam. So if this is your mullion, right, and then this is subjected to horizontal load, your wind load. So basically your beam right here, this roof beam. So this is now more of like a support. And then also right here at the grade beam. So there's a grade beam here. So if you rotate that one 90 degrees, then this is your mullion here, and then this is your loading, right? Uniform loading. So it's the same as a beam, but just vertically loaded, vertically positioned. So the same as you sum up forces, and then this one would if this is H, then this is WH over 2. This is also WH over 2. That's your reaction. So that's your reaction right here. And now it becomes so half of the load will be transferred to the grade beam, and then half of that will be transferred to the roof beam. Now, we'll do frame again. We'll do that here. So so we'll consider only the half to make it more like simple. So the reaction of your mullion is right here. So it will now be acting as well, you can design it as a concentrated load, like, at whatever is the spacing of the mullion, or you can assume uniform load, that's fine. So that would be your, what do you call this one? That will be your, um, lateral load for your beam. And now this one, this is now a, this is now, so this roof is now a diaphragm. So this is what is called diaphragm. So roof diaphragm. Now in this particular building, I am using a steel deck. So this is a steel deck on steel joist. Now to analyze the diaphragm, it's the same, like the same um, theory as if you design a beam, but it's just horizontal. So this is your, say this is your deep beam, and then this is your load. So if you rotate it again vertically, so this is your frame, right? This is your if you look at the plan view, if this is the plan view, this is the roof, right? And then this is the wind load. Now, if this is a roof diaphragm, this is like a deep beam. Now you analyze this one for, you know, bending and shear. So if you get the total W here, again, and then this is the WL, then this will now carry WL over 2, and this is WL over 2 for shear, right? So if you do the shear diagram, it will be like this one, right? Now, this diaphragm, it depends on, that's why I think I already discussed about this in earlier videos where we knew, no, was it, or I think in one of my reaction videos, I discussed about spacing of the um, pathway, um, um, for the like a pattern for the metal deck, how you fasten it. So its pattern, it's either 3/7 or whatever it is. You will have capacity for whatever is the pattern. Now, if you notice, the same as beam, your shear near the support is bigger than the middle. So usually the most stressed metal deck is right here near the support. So, you know, the nailing, or not nailing, I mean, if this is wood, then yeah, nailing pattern. But for metal deck, the fastener in this area, the spacing of your um um pin, or if you're using healthy pins to fasten the metal deck to the steel joist, the the spacing in this area would be closer than in the middle. So the same as if this is a concrete beam, of course, your stirrups will be closer at the support versus the one in the middle third, or middle half, I would say. So it's the same concept as steel beam. It's just that the diaphragm is just positioned horizontally. So the theory is the same. Now, so with this horizontal load, you will now have a reaction here. Now that reaction is the load in this frame. That's the load right there. So you now design this frame with lateral load. So concentrated load right there. So this is pin here, and then this is moment connected here, and then you have now a concentrated load P. Now this load P is from the reaction from your roof diaphragm. So so this is, since this is a still moment frame, then it will be designed as this one, like a portal frame with horizontal load. Now the same concept applies to if this is a concrete frame, like this one at the top. So right here, you know, so all now that's why it is important to determine first the load path. So that was discussed. That was our topic last video, to determine now if, for example, if the walls or the you have horizontal like girts in this direction. Now, of course, the load will be transferred first to your column instead of the usual. If you have a you know, vertical studs, then it will be transferred to the beam. So that's why it's very important to know, like when you start analyzing or modeling, you should know, like, how the loads are transferred to your main structural element. So if this is a steel frame where, like, we have a metal building here. So if, like, usually in a pre-engineered building, you have horizontal girts like this one. So that means all your loads will be transferred to your columns. But if you have metal stud, all your loads will be transferred first to your beam right here. So if this is the framing, so half of this wall is going to the roof beam, half of that will be to your floor beam. And then at the same time, at the bottom floor, the same is going up half of that. So when you analyze this one, if we draw the schematic diagram, so this is the roof beam, this is the floor beam, and then there's another floor here, and then probably a footing here. So that way, that means if you are using say um steel stud, or if we are using hollow block, it depends. Like hollow block, usually it is supported, like you have the main vertical bar for the hollow block, so that means all the loads are transferred to the beam. So if this is, for the sake of discussion, so this is your um if this is your wind load, half of this load will be going to the roof, and then the lower half will be going to your floor. And then at the same time, half of here, right, half of that will be going to the um, upper beam as well, floor beam, and then half of that will be going to this beam here, beam line diaphragm. Now, for so the same as this one here, the same as this one. So you now have a roof diaphragm or floor diaphragm, and then transfer that to the outer frame. Now, for what we call this one, for typical projects, you know, we have all these. These are all column beam, concrete beams, concrete columns, so it's rigid. So everything, like half of the load will be, transferred to this one. The tributary of this column will be half of this bay, and then half of this bay as well. So just like I said, load path. That's the basic, the most important aspect of your analysis to determine the load path. Make sure that you apply the load correctly, because if you put, like I said, if you happen to have a, you know, you analyze the, like I think when you model the roof, or the I don't know, like in what we call this one, I've seen a model where the load is basically transferred right here at the beam as a, you know, I would say probably the resultant of this, half of that. Now, this one is only correct if your load, or you have a girth, you know, horizontal, so that it will transfer, half of that will transfer to the column directly, not to the beam. But if it's the other, you know, other way around, then if you have vertical, you have studs, then half of that load will be transferred to the beam instead of column. So that's why if this is how you frame your building, then you have to apply your load to the beam first, not to the column right away. So you have to identify first the load path. Now, since this is concrete beam and rigid, so everything resists all the lateral loads. And then now in that question, this question here, I would assume, based on our like further discussion, I think what he did was, so this is his frame, and then you have now the trusses here, the trusses like that. So if you are not using the roof as a diaphragm, then um, what happened is, so you have, he said he analyzed the truss as independent, like, independent system. So whatever you get like horizontal reaction from your beam or from your truss, then whatever the result is, apply that to the model. Now you have to make sure that you apply the load at the right location. For example, if you happen, if you happen to have a truss mid-span of the beam, you know, say for example, so if we draw this one, so this is, oh, so this is the frame, and then there's like that. So there's a column here, column, column, column. Now, if you position one of the truss in the middle, then you apply the load at mid-span, not only at the uh, column locations, you know, because I've seen model only with the concentrated loads at beam column junction only. Now, if you have truss in the middle, then you apply the load also in the middle, like mid-span, because that would because what happened now is um in reality, if you have a truss here that transfer the load um through the beam at mid-span, then that beam has to resist that horizontal load. So if you apply the load directly at the column joint, beam column joint, then you bypass, basically you neglect the um, forces that's being carried by the beam, and that's under design now. So you have to apply the load where the load's supposed to be. I mean, if you have a truss in between, you know, then you apply the load. Now, if this is also supported right here laterally, then you have to apply that one also. Unlike at this floor level where you have a now, if there's a roof deck, then that's another story, because if we have a roof deck or like this one, we have a floor, then it will go back to this calculation. This one, you have a diaphragm. So that's why, like I said, um, load path is crucial. Like you have to have, the correct load, or at least identify the load path first before you start your or before you analyze the structure, because um, the result depends on how accurate your load applications are, or your model is. So that's how it's important to know the load path. And so again, so you now have a concentrated load here, including the midspan, or the beam what has to bend horizontally. So that's another um, stress to consider when you design the roof beam. Now, if, like I said, if this is, you have a floor, then um, it will go to this one, like this analysis where you have a floor or roof diagram, then transferred to the your beam columns, and then down to the foundation. So that's if you have a beam column system for lateral force resisting system. Now, this one, in this example, there is a shear wall. Now, you already identified how the loads are transferred to the, or you already know how the loads are transferred to your element. So, in this particular example, instead of your beams and columns resisting the lateral force as a, rigid, like, movement frame, this one, you rely on the shear wall. So this is only showing in one orthogonal direction. So there has to be a shear wall also. If not, then it will be a hybrid, a shear wall in this direction, and then moment frame in this direction, which is unusual, but it happens. So instead of the beam and column resisting the movement frame, the lateral load, it is now the shear wall that transfer the load down to the foundation. So for shear wall, um, because there like someone messaged me also like months ago. I just can't find the his original message because I delete messages from time to time because there's there are lots of um, PM I receive like every day. So I keep on deleting like from time to time. I will just keep the new ones. So for this particular frame, so like I said, you have no share wall. If this is a going back to that guy who messaged me, so basically he was asking how to analyze a concrete shear wall. So I told him like if the best way to understand shear wall is if you study the wood shear wall. If you understand the wood shear wall, I would recommend to study this one if you want to know shear wall because this is way more complicated than concrete shear wall. But we will discuss about that later because there are ways also how to analyze a shear wall. So the next topic would be if this is a steel frame. So if this is a steel frame, like this, so for example, assuming this is a steel frame, the same applies for steel frame, but instead of shear wall and also moment frame, because it would be real if you use moment frame in steel building, it's gonna be expensive versus if it is a braced frame. So if this is a steel frame, this one, assuming this is steel frame, now you already know how the loads are transferred. So instead of rigid connection here, because this is concrete or shear wall, like this one, all you have to do is assume a cross bracing right here. Now the cross bracing doesn't have to, you know, have to be at every bay. You can have one bay only this brace. Just for example, in this floor plan, you can have this bay as braced bay. You don't have to have this as a braced bay also. If this is enough, then you can have just one, and then this one another. Now, most of the time for steel frame, we will not brace every bay because that will restrict movement. I mean, imagine if this is supposed to be an open space and then you have cross bracing there, so you have to identify. So in the when was that? Um, I'm sure I already discussed, talk about this one with regards to aspect ratio. So we already talked about aspect ratio for the um, diaphragm and also shear wall. Now for example, if this is a steel frame, if this whole width like this one, if this whole width of the building versus this depth, if this meets the aspect ratio, then you can have cross bracing at its end only, like right here. At the same time, in this direction, you can have, full width so that you have a free space in the middle. You don't have to put the cross bracing. Now, if this exceeds, for example, if if this exceeds the aspect ratio, then you will be forced to provide interior cross bracing. Now, there are different types of bracing. So first is this one, cross bracing. And this type of cross bracing, this bracing resists both compression and tension. So you will see this one like a WT section or HSS, or could be a pipe, no, pipe section. And then this one will resist both compression and tension. Now this is called the inverted V braced. Uh, this one here. I've seen steel building with this kind of bracing, but this one is the most common next to the this one here. Now the other one is diagonal brace. So this one resists also compression and tension. This one also, if the load is in the direction, this one is in compression, and this one is in tension. Now, if the load, for example, is in this direction, this is in compression and this is in tension. That's why you need a more rigid section to resist the compression. Because imagine if that's just an angle, then it will buckle, so it will be useless against compression load. So this has to be a rigid also. It could be W section, W section or HSS or pipe. When I say HSS, that's the rectangular or square tubing, and then the pipe. It's this one is still called HSS, hollow steel section. Now this particular type of bracing only resists tension. So this is a tension rod. It could be a cable or a tension rod. So it only resists tension. So for example, if this is your load in that direction, then only this member resists the force. And then this will be in tension, right? So this is in tension. Now that tension will be resisted by this horizontal member, which is called the strut. So this strut will be subjected to compression, and then this compressive force here will be transferred again to this diagonal in tension and then down to the foundation. So these are the member that are subjected to the forces if the load is in this direction, and then vice versa because the wind can be in any direction. So if the wind is in this direction, then it's the opposite. So it's this one here that resists the load. This is also resist compression and tension. But I've never seen in real life. I've never seen this kind of bracing so far. Maybe I mean, I just I haven't seen, especially this one also. I haven't seen that kind of bracing in actual practice. Maybe in other cities, I don't know. But the most common really is this one here. This one, this one also that's common, and then this one. This one here is not so common because what happened on this one is you will have really big, force at that junction there. I mean, it can be designed, but I've never specified this kind of bracing before. This one I did most of this one and this one. So in my practice, I only use these three types of bracing. Now, shear wall, this one here. So if you are using shear wall like this one here, mm, so we have these types of shear wall. Now, I will discuss this as if this is a wood shear wall because it is way more complicated to analyze a wood shear wall than a concrete shear wall. I mean, me personally, I think wood shear wall is way more complicated than concrete. Um, in concrete, you can model that as part of your, when analyze using a software or there is actually a software used for wood shear wall. It's by Woodworks, but I've never used that one. When I analyzed that six-story wood frame building, I did it manually by hand. I just made a spreadsheet. Now this one, um, I don't know if this applies to concrete shear wall also. I'm not sure, but there are three types of shear wall. You have the segmental or segmented, and then you have the perforated. Now, this perforated, this is um, typically for um, wood shear wall. I've never seen a what we call this one. I've never seen a um, perforated. I mean, discussion about perforated concrete shear wall. It's always wood frame, wood shear wall. And then there is a. I mean, these are the types of like how you analyze a shear wall. So you have segmental, you have perforated, and then the third one is the force transfer around opening. Now, for segmental or segmented, so for example, you have opening here, like this one, like these walls have opening. Now, when you say segmented shear wall, you only consider the solid walls. So this one, you only consider solid walls. So this part here. So you only consider that part. That is the segmented shear wall analysis. So this one will be a separate shear wall. So you say this is shear wall 1, and then this is shear wall 2. And then the force will be divided depending on the stiffness of this two. Now for wood shear wall, what you or what I typically do is, for example, if this is say this is 3, and this, say for the sake of discussion, this is 3 feet, and then this is 7 feet, and then the load is 10, right? 10 kips. Just for the sake of discussion. Therefore, the total the, to- therefore the total length of your shear wall is 7 plus 3 is 10 feet. So therefore, if your load is 10 kips and then you have 10-foot solid wall, and this segment is 3 feet, then that means this one carries 30% of the load, or this carries 3 kips, and then this one is 7 kips. So you just distribute the load based on the length. So you divide the total length, or you divide the load by the total length times the length of the panel. So this one. So this one resists 3 feet, 3 kips. This one, if these are the same width, say for example, this is 5, this is also 5, then of course this shear wall 2 and shear wall 1 is equal, and then each carries a 5 kips or 5,000 pounds each. So that is segmented. And now when you analyze that one, of course, this is considered as a separate shear wall. Then you analyze this, like, from shear, and then overturning, and then bending, and then deflection as a separate wall, separate system. And then if you have something like this one here, the same, no? So this is also one panel, and then this one is also one panel, this one, and this is also one panel, provided this panel length, this one meets the, again, aspect ratio for shear wall. Now, if it is uh, block shear wall is 3.5, I think. So the ratio of height versus width is, so if you divide h over w, this should be greater than or equal to 3.5 before you can consider a particular wall segment as shear wall. It has to meet the aspect ratio. If I remember correctly, this is 3.5 for wood shear wall block. For unblock, I think is um, 0.5, like 5, I think. I can't remember exactly because I never use unblock shear wall. So that is segmented. Now, perforated. This this perforated analysis is more of a what's the term for experiment? Empirical. So So this method, this is actually a empirical equation, empirical method, and developed by a Japanese engineer. So for perforated shear wall, you can analyze this one as solid, as one whole wall, because like um in segmented shear wall, like the one we discussed earlier. So for example, this is one segment, right? So this is one segment. This is one segment. If this is a segmented shear wall analysis, that means you need a hold down here at each in post. So the same right here. So if this is another one here, then you will have hold downs like that. Now for perforated shear wall, you can analyze this as one whole wall with the opening, and then your hold downs will be right here at its end only. And this one will usually gives a smaller hold down. So there will be smaller force here, like for the tension on the uplift at that joint here. It's usually smaller than a segmented. But the capacity will be reduced. There will be, for example, it has to meet a certain criteria like the ratio of the height versus the opening, and then there's a like a table that you can use as a guide. If this ratio is that value, then you can use, say, in the table you can use 80% or 70% or 60% of the total capacity. So that's perforated, and this is more of like experiment by a Japanese engineer. And I've never seen that method used in concrete. It's only used in, or maybe other engineer used that in concrete shear wall analysis. But this is so far what I've read. This is only for wall shear wall. And to be honest, I've never used that specific method. I only use segmented and force transfer around opening. Now, the only difference with this force transfer opening is more of like a hybrid between segmental and perforated, and then it considered all the forces by the name itself, force transfer around opening, because you analyze this one as the same full panel with the opening, and then you technically or typically analyze the tension right here. So you will see strapping right here, top and bottom of the opening. And the analysis is, I would say, not not easy, but not too complicated. It follows the simple mechanics. So if you have the load here, now you can analyze the tension right here, and then compression right here. And then if you follow that force, that's the same force going all throughout here, because that's the resultant. So the 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 only difference is at this location, because there's an opening, this portion of the wall carries more of the, or much higher shear than the solid one, like this one here. So whatever's the reaction here, you divide this by this height, total height, and that is the shear force at this one in, say, pounds per foot. And then you compare that with the capacity for shear wall. Whatever the spacing, you can have 6 inches on center nail, or 4 or 3 or 2 inches on center. And then this one, you will expect a much farther, spacing than this area here. So that's the force transfer around opening, and then you analyze this strap to transfer that load because this area here will be subjected to compression and tension. Now, if you really want to learn about this one here, you can search that in YouTube. Um, wood shear wall. I think Woodworks has discussion about that one. EPA, and then what other FP innovations. I think in FP innovations. So you just type even this one force transfer around opening. There's a discussion in YouTube on this one, but it's not really detailed. When I studied this, because before when I was still in the Philippines, all our shear walls are designed using segmental. But there is no problem about um, wall panel or solid walls because it's a hotel, and then you know yes, of course, every room has window, but eh, we have enough solid walls to not consider this analysis. So in some areas, especially say there are apartments that the like especially small buildings where you have only few feet left for solid walls in like in one side, then most of the time I will be using both segmental and force transfer around opening when I design share wall for smaller houses like apartments, smaller buildings, or commercial. So yeah, if you want to learn more on that one, you can Google that one there. So again, like well, we will discuss also like the parts of the diaphragm. So again, we already discussed right here. So you have the roof diaphragm and then the load laterally. So you have so assuming this is your roof diaphragm, and then this is your loads, right? So like any other beam. So instead of like beam, usually if this beam, then you have column here. But since this is shear wall, yeah, diaphragm and then like horizontal like diaphragm and then shear wall. So you will have it's either your lateral force resisting system could be bracing right here or shear wall or moment frame. So this is still the same analysis. And then right here. So this one you will have if this is like any other beam, this one will tend to deflect, right? So it will deflect. So this is just an exaggeration, but this is the deflected shape of the diaphragm, especially if this is a wood diaphragm, then it will be flexible, so it will deflect more. Now, like any other element, so if this is bending this way, but this is simply supported, or at least for wood shear wall, it's always assumed as a flexible, or not always. Some codes will ask you to really calculate or determine first if it's flexible or a semi-rigid or a rigid diaphragm. It has something to do with deflection. So, but in some code, you can always assume like all wood frame will be like wood diaphragm will be flexible diaphragm. So this one will be subjected to compression like any other element if this is bending. So neutral axis right here. So above the neutral axis is in compression. This was is in tension. Now this one are called chord. This is compression. This is chord in compression. This is chord in tension. Now that's why right here you will have to analyze the because you cannot have, for example, if this is say 20 feet, you cannot have a wood top plate, or if you are using a metal deck. So that's why in metal deck, at each end of the metal deck, you typically have some kind of like that. If that's your metal deck, this is a perimeter angle. Now this perimeter angle, usually it's called pore stop. No, pore stop, but the main structural function, other than well, the name itself, stopping the concrete from falling that way. So you have to have that angle. But one of the structural function of this pore stop is the to resist the tension. So that's why in metal decking it is important to have this perimeter angle because that will serve as your tension. Now if or to resist tension, if the load is in this direction, then this is the one in tension. That's why it's all over. I mean, it has to be around the perimeter because without that one, you will see tearing. Imagine you have load, and then this is in tension. Then metal deck are just really thin metal, so it will tear. You know? So that's why you have to have that what we call this one perimeter angle. Now this member here transferring the load to the shear wall. Like if this is diaphragm, so this is the cord. This is called the collector. So that's called the collector, or sometimes called strut, and it's always in compression. If the load is in this direction, if the load is in this direction, now this becomes the compression cord. This is a tension cord. Now this is the strut. So that's why you have to have a perimeter angle. Now for wood frame, this could be your rim board because the typical section is of a wood frame. You have your sheeting, and then you have your bottom cord from walls above, and then this is the rim board, and then this is the joist, this one, and then you have another top plate here. Now this cord, you can analyze the rim board as your cord, and then splice that one because of course the whole, like I said, if this is 20 feet, you have to have like a splice somewhere, you know, because that would not be a full length 20 feet. I mean, if it's engineered wood, yes, you can go up to 40 feet without cut, but for um, dimension lumber, you can, I think, in hardware, you can get up to 12 feet, but if you go directly to the sawmill, you can go up to 20 feet, sometimes 24. Some contractors, I've talked to them, and they say they can order up to 24 directly to the sawmill also. So if that's the case, if this is the ringboard and you have um, a joint here because you cannot have a full length, then you have to provide like a tension splice there. So you can use strap, metal strap to splice this one here. Now the same with if you are not using the ring board, then you can use the top plate. And then the same, the top plate, usually the what we call this one, the splice is staggered like that, and then this one is staggered like that. So you can fasten this one, right? But if this fastener is not enough for this, for the tension caused by this by the bending of the diaphragm in that direction, sometimes we specify a strap also connecting the because what happened now is if your connection is just the staggered splice like that one. Now the effective section that resists tension is only actually just one ply, even if you have a two ply top plate, because at this joint, you know, there's no connection here. It's just butt against each other. So you rely on the nailing on this top plate, and your effective section that resists the tension is this section only. That's why if the load is big, then all we have to do is, instead of relying on the splice of the like nailed splice, we will use a strap also, that one. So that's for the diaphragm. Now, once you determine the forces on this one, like the other beam, like, design for shear, calculate for shear, you will have shear diagram, and then you will have also the um, moment diagram. And now the moment, whatever is the moment here, whatever is the moment divided by the depth, that's your compression here and tension. So the init like the same if you have a, say, steel section, right? So if you have steel section, W section. So if you are doing, say, moment plate, like a splice plate right here at the top, so to design the tension on the plate will be whatever is the moment divided by the depth. So the same concept as this diaphragm. So once you get the reaction, you will apply that to the shear wall. So the shear wall is like this one. So it will be, like I said, designed as a either segmental or this one. First, when I do analysis for shear wall, I always use segmental first. And then if the wall is not enough, that's the time I will use the force transfer around opening. And then if it doesn't work, for the, you know, just sometimes it just won't work. So first would be request the architect to add more solid walls. I mean, you're talking about reducing the width of the window or maybe eliminating a window. Like for example, the load right here is smaller than this here. In this floor will be smaller than this one because this one accumulates the force from the upper floor and that floor level itself. And then the lowest floor will resist the whole, you know, the whole load, like from top, from the roof all the way down. So that's why sometimes in this um, um, situation, sometimes we will ask the architect, okay, can we remove this opening, or for example, instead of having a, for example, this is your window, and then you will have window here and then window here. So this particular wall will not meet the aspect ratio, so you will be forced to use just this portion here. But if you move the window in this direction so that you can use this portion, you know, or if not, if you can move, you can adjust the window so that all of this like this segment here, can be used as a shear wall. Make sure it will meet the aspect ratio. Then that's better because you now have a full length of your shear wall panel, and then you can reduce the uplift because it's, you know, if the force is right here, of course, when you check for overturning, this is will be because this one is spread, like really far apart, then you will have smaller forces right here. And then you are utilizing the entire wall with, the force transfer or opening. You just add strap at the top and bottom of the opening. So that's how that's why if you really want to know about shear wall, the theory is the same regardless of what kind of material is it, whether it's concrete or wood. The theory is the same, but the like, to me, I think it is better to learn or study shear wall um, with wood because I mean, everything. I mean, like the analysis is Like I said, when you design a commercial wall, all you have to do is just model it in a software if you're using a software. But for wood, it's all, you know, like hand calculation, and you will be really, you know, to me, it's interesting to design this one like wood share walls. Um, well, like I said, it is it is not so complicated, but it will really give you headaches. And so yeah, what else? Uh, let's check. So we have moment frame, portal frame, wind column. Now, wind column is basically just a cantilevered column because I've used this one, I think, once or twice only. Because um, what happened is, it. I think the project was a garage, and then if you have a garage like that, they want this whole thing like as wide as possible, where this whatever is left here will not meet the aspect ratio. Because if you look at the elevation, um, so for example, this is your building, then there's your roof, and then they want a large overhead door so they can fit, big trucks going in and out. So this is an overhead door. So there's no more room here for shear wall. So I think I already posted this um, regarding a portal frame, but that was wood. So I designed this as a wood portal frame. That one. In that particular example or particular project, the wood frame works, but I have to have two portal frames because there are two overhead doors. There was, I think, one or two projects where this frame will not work. Like like this is too wide. This one, I think this was 30 feet. I think 30 feet or 25 feet. And then if we use a portal frame, this is just too. This will require like a really deep section, and it won't work. In the headroom here won't work. So what I did was a wind column. So wind column is, for example, this is your. I'm really bad at drafting. So so this is wall, and this is your that one. So this is the wall, like this is the overhead door. So portal frame is not an option because it won't work. It's too big. So what I did was I designed a wide flange here, wide flange column. And all it does is just to resist. This is a cantilever. This is a movement at the base because this is a cantilevered column. So if you look at the elevation, this is the wall, right? And then this is right here. It's just, it's just cantilevered column, and it will resist the reaction from the roof diaphragm. This is um, basically a cantilevered column with concentrated load. So if you rotate that one 90 degrees, it is now a cantilever with concentrated load. So that's how you analyze the wind column. So instead of beam with vertical load, it is a column with horizontal load, concentrated load. So this only resists windward. So because you have windward here, you have leeward, but leeward in this direction, but the wind can be in the other direction. So this could be leeward now, and then this is leeward. So that's why one wind column will be designed just the windward. Because if this can resist windward, then if it's the same section, then this should be able to resist leeward because leeward is always smaller than the windward. So design that as a cantilever column. This will be a moment frame. So that's what a wind column is. So it's usually used, you know, for large openings, and you don't have room for a portal frame, or you have whatever left, like this wall here doesn't meet the aspect ratio. For example, this is only 2 feet, and then the height of the building is usually for garage is only 20 feet. So that's only like what, um, 10%, like point 0.1, right? So it's only point 0.1 instead of the usual 3.5. Now, if you use 3.5, this one divided by 3.5, what, like 20, 3.5. So you need 5.7. So this one should be 5.7 something, so 5.8 feet for it to meet the spec ratio requirements before you can use that as a shear wall. So that's what the portal wind column is. And what else? Um, Wind column, moment frame. We already so yeah. So that is about lateral force resisting system. So when you design, I mean, it's really up to you what you want to use, what kind of system. If it's concrete building, then you can use, you know, just moment frame, the typical conventional way of framing a concrete building, just beam and columns and have that, resist the lateral load. But in mid-rise and high-rises, concrete frames, it's usually a shear wall, and sometimes it's the elevator shaft that will be used as a shear wall, and then sometimes right here at the corner, this will be a shear wall, you know. So it depends. And like I said, for the roof diaphragm, if you are not using your roof as a diaphragm, then all your load will be transferred to the beam as a horizontal load. But if you are using the roof as a diaphragm, then all the loads will be resisted by the roof as like this, and then transferred to the outer frames right here, uh, right here. So it depends. So whatever is, um, you know, whatever works in your system, like in your structure. Of course, if you are using, you don't have any solid walls, then you can use the to resist this lateral load. So if you are using just the beam and columns, that's why you will have really big sections, like large sections of columns, large beam sections. But if you have shear wall, then you can have smaller columns and beams because you rely on your shear wall for the lateral. So anyway, yeah. So if you have any questions, just comment. If I missed something, just comment, or you can message me, and then we'll discuss that. We'll do like a follow-up video. But I hope this is clear enough. And yeah, so like I said, to recap, first thing, determine the load path first before you even start modeling or applying the load to your structure, so that it you know all the loads are transferred properly and correctly. So I think that's it for now. And once again, if you can join our group, so we are growing. mm, We are growing. Um, Join our group, Structural Engineering for Dummies. So yeah, I encourage you to join the group so that we can share and learn together. Okay, bye bye.